All right, Cameron, you had a question?
Yeah. It was on the solving two equations and two unknowns.
Uh-huh.
It was the like part F. I don't know if you can like look at it or if you want
Give
me
me 2 seconds, let me pull it up.
to. Okay.
Nope, wrong class. Okay, so what question number?
F.
Okay.
For the solving two equations and two unknowns.
Okay, so I'm on that question. And part F. Okay, so what is your question on that?
I just like, I'm not sure if I'm setting it. I don't know how to like set it up. Like, I just don't know how to get to where I need to get to, I guess.
Well, no, and it's a great question. So let's go ahead and actually do that. So you have F cosine theta minus mu it's normal equals 0 and F sine theta plus normal minus mg equals 0. And so this one, the only thing we want to get rid of is our normal, this variable here. Is this the question you're talking about?
Yeah.
Okay, so my suggestion to students with this is when you are told, this, we don't want this variable, or you have too many unknowns, so you want to limit one. And as we work through things and do this more and more, it'll become more comfortable. Is what you want to do is solve for the variable you want to get rid of. Because then I'm going to say something to the effect of, and I'll start with this equation right here, that the normal equals something. So I'm going to move everything else, this and this, to this side of the equation. So I'll get then the normal equals mass times gravity minus force sine theta. And now keep in mind right now, these are just letters and variables. You don't know what they are, and you will get to know them quite comfortably as things move on.
Are you able to show us what you're
doing?
doing?
I'm not. Oh my goodness. How did I get out of the swing of things that fast? All right. Yes, throw things at my head when I appear to be writing and I'm not actually sharing. How's that? All right. So move everything to one side of the equation. Just start with the easiest thing and then look for the next thing. And then I'm going to go to this equation now. I'm going to do the same thing. I'm going to solve for the normal. So my thing is I don't like negative signs. So what I tend to do is move the thing that's negative to the other side just to make life easier. So then I'll have mu s times the normal equals force cosine of theta. But to do two equations with two unknowns, I need to get rid of this coefficient, this mu s, this thing that you don't know yet. And the only way to do that is to divide both sides by it. So that's going to give me an equation that says that this normal equals force times cosine of theta divided by mu s. So now I have two equations that equal the same thing. If I'm solving a system of equations, if the two equations equal the same thing, I can set them equal to each other, and that's exactly what I'm going to do. So then I'll give me mg minus f sine theta equals f cosine theta divided by mu s. Now, before I do anything, I ask myself, what is the thing they want me to solve for? And they want it to give an expression for force. So I need to get whoops, that is not what I wanted. Here we go. I want to get force on one side of the equation and everything else on the other. So then the trick there is to get the things that have this force, this variable in it on one side and everything else on the other. So I'm going to move this one here to the right side. So that'll give me mg equals f cosine theta divided by mu s, and then plus f sine theta. Cool. I want something that says f equals. This is what my goal is. So how do I get to that from where I have things now? Anyone?
You have to simply, you can't simply divide out f from the right side, can you?
So you're really, really close. How would I divide it out if I wanted to?
You'd have to deal with the over ms or mu s.
Okay, okay. So you're really, really close. Okay, so you're saying, all right, let me go
Thank
ahead.
you. That's the word. Factor.
Mu s times mg. Whoops, can I do that? I was just going to move it randomly.
No,
No, why? What's wrong?
because
You have to apply it to f sine theta as well.
Yeah, it doesn't live there.
So you
Yeah.
multiply everything by mu s, and then you can factor out the f to the left side, correct?
Yeah, so you can do that. There's nothing wrong with what you're suggesting. My habit is to go like this, to say, I'm going to do what we call factoring out. So I'm going to pull the f out of this part of the equation. Cosine theta over mu s plus sine theta.
I forgot that's a thing you can do.
It's a fantastic thing we can do, and you're going to get really used to it. So I look at this and I'm like, okay, I'm going to move it to the other side. There is no, you must do rule here. But when I have a fraction, if I'm dividing by this whole mess here, it is so much easier to do if this whole thing here is one fraction. So I'm going to do the exact step that I didn't see who was recommending it, that the voice on the other end was saying. I'm going to get my common denominator. I'm going to multiply sine theta by mu s. So I have everything over mu s. Does that make sense to everybody? Okay. So then that'll give me cosine theta plus us sine theta divided by mu. All right. Now I am ready to isolate force and have just one single expression. So now what do I do?
Just divide by cosine
Yep.
theta plus mu.
Yep.
Sine
Yep.
theta over mu.
And now here's the thing, and I'm going to say this up front. What I find is a lot of first quarter physics students are reluctant to say that they're not comfortable with fractions because they've been doing calculus. And so it kind of feels like they should be. And here's the thing. If you don't use a tool a lot, then it is really easy to become uncomfortable with that tool, and we become dependent on our calculators. So I'm going to show a lot of steps to make sure we get really comfortable with manipulating things that have no values in them, because that is a skill you will have to have moving forward. So we're going to start today. And my reminder is that if I divide by a fraction, another way of saying that is I'm going to multiply by its inverse. So I'll have mu s over cosine theta plus mu s sine theta on the bottom. All of this times mg equals f. Does that step that I just did make sense to everybody? Any questions on it? So if you do have questions, feel free to set up office hour times if you want to work through more of these and get comfortable with it. Now for mastering, what I can say is they don't want this form. They don't want parentheses everywhere. So now we can just distribute the mg. So my final form would be like this: mg mu s over cosine theta plus mu s sine theta. And there we go. So going back, the first thing you want to do is isolate the variable that you want to get rid of. So set everything, get everything to where I have my normal equals, or whatever the thing is that I'm not going to need, make sure I set everything equal to it. Then I can set the two equations equal to each other. There's also another approach that you can do, but as most of you haven't had linear, we're not going to go into kind of doing the systems simultaneously with linear algebra. Or you can set one equal to the normal, and it kind of gets ugly. Once I've done this, the other thing I can do is take this whole thing and say this is what the normal means and plug it in here.
Would you mind showing just how you set that up? You don't have to solve the whole thing, but I'd be interested to see it.
Sure. So I'm just going to copy paste. Let's clean this up. Come on. Ah. All right. So then I did let's pick one. We'll just go normal equals mg minus f sine theta. So the other option there is to go ahead and substitute this one into the first equation. So I get f cosine theta minus mu s times mg minus f sine theta.
Oh, sorry, I see what you're doing there. I meant the linear algebra.
Doing a
System.
system simultaneously?
If you could just write the system, like I just want to see
Yeah,
the.
okay. Sure,
Okay,
sure,
thank
sure.
you. Sorry.
Sure. So, with variables, what we want to do with linear is I want to make this thing cancel out. So I have a negative sign up top and a positive sign on the bottom. So if I wanted to solve this as a system, what I need to do is make these two quantities exactly the same. So I can do that either by dividing the first equation by mu to make it to where I have just the normal alone, or multiplying the second equation by mu to where I have identical quantities there. So then that would look like f cosine theta minus mu s normal equals 0, and then f sine theta mu f sine theta plus mu s n minus mg equals 0.
Wouldn't it be
And
mg mu?
Oh, yep, thank you. And there's an s. Let me make that neater. Equals 0. So I'm just adding these two equations together.
Got it. That makes sense. I've seen that approach before.
Yep.
Thank you.
So there's more than one way to do this, and this is actually a great time to point out that if you do something one way and somebody else does it another, that doesn't mean you both are wrong. And that's probably one of the bigger challenges in physics, is that there are so many ways to do the exact same problem. Okay, are we good with that? Any
Yes,
questions?
thank you.
Thank you for asking it. That was a great question to ask. And yes, at the beginning of lecture, this is the time if you have those, because it allows for more interaction, and I guarantee that you weren't the only one thinking that one through. And that skill right there is a critical one we will use throughout the quarter. So if you get stuck on it, please do let me know. All right. Any others before I move on? And I just realized something. Okay, I am recording. Cool. So I have posted a video on all of the terms that we're going to use. What I just want to take a minute to do is to kind of go back over and hit on some of the most important pieces to take out of our terms and the fact that we're working with vectors this term. One of the most critical pieces that you will see, and it's the question I asked on the handout, from watching the video lecture, can anybody give me an explanation on what a positive and minus negative mean as far as vectors go?
Would that be the direction of the vector?
Yeah. So now let's take that in terms of velocity. So if I have a negative velocity, does this say anything for me? What does this mean?
It really only specifies direction based on whatever coordinate axes you're using.
Perfect. Whoever just said that, absolutely. So the reason why I bring that up is we're going to get into negative acceleration and negative velocities. And what people tend to do is assume that negative acceleration means you're slowing down, or that negative velocity means that you're slowing down. And all that says is that I have some random vector and I get to choose how I'm defining positive and negative. So I can do this. You'll see me doing it as we move on to two-dimensional motion a lot. I'll say, okay, I'm defining the standard as positive and negative. So if I have a negative velocity, that means that my vector would be going this away, not this away. But sometimes it's handy to change these things. And we can say, you know what? I don't want to deal with those negative signs. So I'm just going to do the exact opposite and make the other directions negative, flip things around. And now if my vector is going this way, this one is a negative quantity. It's bad to point with a vector. So our positive and negatives only give us direction. They don't actually tell us anything about the motion, whether something's speeding up or slowing down or going back to home. It would depend, is home in the direction of what I've defined as positive, or home in the direction of what I've defined as negative. So if anything that you can take out of these first couple of days, this here is like by far one of the more important ones. The other thing I want to point out is this concept of displacement. And we are going to be working with vectors, which means that's what we're looking at. And the one example I like to use is if you get on a treadmill and you run for an hour on the treadmill, unless you started at the back of the treadmill and ended at the front, your displacement for that entire hour would be 0. You would have gone nowhere, because displacement is a vector quantity. It's only looking at the distance between, the shortest distance between where I start and where I end. That one tends to be a little bit tricky for folks to get their heads wrapped around. And going forward into your homework, I want to emphasize this difference between average and simultaneous. If I want my average velocity, I need to find out what my total displacement is divided by the time it took me to cover that distance. That would give me my average velocity. Now, in the case of the treadmill, my instantaneous velocity then, and we're going to get this on graphs, so it'll be a little bit easier to see, is going to be literally how fast am I going at that split second in time. And looking at it on graphs makes it easier to see. But what people tend to think is that they can go your final velocity minus your initial velocity divided by the total amount of time or displacement that you've gone, or divided by 2 tends to be like the most common thing that people will grab onto. But if I'm talking average velocity, it is my total displacement divided by my total time. Are we all good with that? Okay. Weight in newtons, that one there tends to be really confusing to people because it's contradictory to the language we use every day. So it's one that you want to remind yourself of. Weight in newtons, and this will make sense as we move on a little bit further, is going to be your mass times gravity. This thing here is our weight, not in pounds. It drives most of us crazy because folks will use pounds as force because you see it so often and just day-to-day language. So force yourself to define those things in terms of what we are using, not what you are using. That's probably the most difficult part when we first start, is getting rid of language that we use every day. And acceleration is another one. Slowing down is also acceleration. Speeding up, acceleration. Changing directions, acceleration. Anything that moves me off straight line motion requires a net force. That net force results in an acceleration. And we're going to define that more specifically as we move on. But for now, just remember, acceleration is just a change in velocity. It doesn't tell us whether or not we're speeding up or slowing down unless we have more information. Now, today's piece, well, actually, before I do that, any questions on the terms above?
I just wanted to specify real quick, just because it's been a while. Newtons then are kilograms per meter per second, kilogram meters per second.
Yes.
Okay.
Yes. So it's going to be, let's see, I'm going to have a force net. It's going to be then mass times acceleration, which you are absolutely correct, is kilograms times meters per second squared. Where this piece here is your acceleration. Are we good with that? Does that answer your question?
Yeah, that does. Thank you.
You're welcome. Somebody has an open mic.
Justin.
Justin.
Thank you, Justin. And don't worry, it's happened to all of us at some point in time. And real quick, before I move on, I want to emphasize this, make a sticky for yourself and put it somewhere that only a net force equals MA. We cannot define every force in the world in terms of MA. I can't just write this. And when we get into forces, I'll be more explicit on why that is. But for now, file that away in the back of your memory. So now here, whoops, is what we're going to do today in terms of graphs. And we're going to bring in our motion to the graphs themselves. And this is something I tell everybody to do, is to get in the habit when you're working problems, doing these guys. Just take a couple seconds and scratch them out. And actually, let's not do, we don't need 3 dimensions or 2 dimensions. We just do this. And I'm just going to start with this one I'll call position in terms of time. This one I'll call velocity in terms of time. And this one I'll call acceleration in terms of time. And let's remind ourselves what the units on these things are. So this is units of meters. In physics, everything in terms of time is in terms of seconds. Let's see, velocity is meters per second. Acceleration is meters per second squared. Go ahead and be consistent. And then just draw a straight line. Like, let's make a nice little 45-degree line. Because one of the things that a lot of students struggle with is remembering as we go into the calculus is something, do I need to integrate something to get to an answer? or do I need to take the derivative of something to get to an answer? And by doing these three little graphs real quick, you can remind yourself of exactly what direction you need to do to get to the quantity that you want. And sometimes we need to do more than one step. Sometimes I need to integrate twice or take two derivatives in order to get to an answer that I want. And the way I can look at this is say, okay, so what is the slope of the line? How do I define slope? What is that? Just in general.
Like the tangent of the line or the rise over run.
Rise over run. Yeah. So both are true. Both are correct. Rise over run. Or you'll see it written, let's see, rise dy dx. Or in this case, let's see, this is where it gets a little bit confusing. My y here is x, right? So if I'm looking at the slope, it's going to be my change. Actually, I'm going to erase this so it's not visually messing you up. So I'm going to have my change in my position here over my change in time. So what units does that give me? Units of displacement are in meters and units of time are in seconds. So the units for this slope are meters per second. What quantity is that? What physical quantity is that?
Speed.
Velocity.
Velocity, perfect, perfect. And the only difference between speed and velocity is that I have magnitude and direction. Remember, one is a scalar and the other is a vector, speed being a scalar and vector, velocity being a vector. But otherwise, correct. It does give you those units. So if I take the derivative, I am just looking at the slope of the line for wherever I want that information from. So a derivative is nothing but determining the slope of the line. And it's going to get kind of fancier looking where it's easy to forget, but that's all we're doing is taking the slope. And I'm not going to do the area under, I'm going to save that for over here. So let's see, this would be for an x versus t. Now let's do velocity versus t. My slope there then is going to be my change in velocity over my time. Let's see. So my units there, this is meters per second times 1 over seconds, otherwise known as meters per second squared. And what quantity is that?
Acceleration.
Yep. So that means the slope of a velocity versus time graph gives me acceleration. Or another way to think about it is I'm looking at how my velocity changes with time. If my velocity is changing, then I have to be accelerating. Otherwise, my velocity wouldn't be changing. It would be constant. So the slope of that line tells me the rate of change of the velocity versus time. Therefore, the derivative of a velocity function gives me the slope. I'm sorry, gives me acceleration. Now for this one, let's take a look at the units here. So for under the graph, I'm going to have, let's see, the area under the graph. I'm going to ignore the 1/2 for a minute because that's just the area of a triangle, just so you remember. Triangle, 1/2 base times height. For purposes here, so it's not overly cluttered, we're just going to go with base times height. So base is in seconds. So for my velocity area, what do I have? I have a base of seconds times my height of meters per second. Seconds can't cancel out, and I am left with units of meters. So this area here, my integral then, is the area under the curve. And so my integral here gives me displacement. And we use these fancy symbols that look like this. Well, that symbol is really just a fancy S. And what it says is I am taking these infinitesimally small little slices of this area under this curve and adding them all up. I'm just taking a sum. So this is my integral. Are we good with that? So if I have a velocity function and I integrate it, that in effect gets me back to my displacement. And I can do the same thing with my acceleration. I can look at the slope of that line. So for acceleration, I have the slope is meters per second squared times what? Rise over run. Oops. Oh, yeah. No, I'm good. Meters. Rise. Second squared times seconds. There we go. So this is the slope of this line. Now, does this unit look like anything useful?
It's rate of acceleration, right?
Yes, the rate
So
of
it's
change.
jerk.
Yep, it's the rate of change for acceleration, which is something that I will only have you demonstrate numerically just to show that you know how to do the derivatives and the integrals as we move on. But as far as applying the physics, it gets quite complicated. So for our physical analysis, as we move on beyond exam 1, you won't be seeing this. This is called the jerk. And it's very realistic. If you consider just driving down the road, your acceleration does not stay constant. So if you've ever gotten in the car behind or with somebody who's not driven before, and they're doing that, hitting the brake unevenly, or doing the same thing with the gas pedal where they hit it, pull their foot off, hit it, pull their foot off, and you feel yourself moving back and forth, you are experiencing the jerk. You're experiencing acceleration that is changing. Whereas a smooth motion of braking, so a constant acceleration slowing you down, or your foot on the gas pedal smoothly going down, so a constant acceleration speeding up, you can think of yourself as just resting all nice and peaceful like. So the slope of acceleration is not something we're going to deal with much in this class because it takes it to a whole nother level. But we get to this unit adding all these little pieces up. So the slope here equals the jerk. And you can remind yourselves that we're not going to use it much other than to practice it mathematically. However, you will be entertained to know that there is a snap, crackle, and pop as well. True statement there. Now I can look at the units here. Let's see, this is area again, meters. God, I got my hair stuck in my hand. Meters per second squared times seconds. That cancels, that cancels. So the area under an acceleration curve gives me velocity. The integral of an acceleration function gives me velocity. If I want to know the displacement resulting from a certain acceleration, then let's see, I would integrate and I would get to this velocity function. Excuse me, and I'd look at that and say, okay, so now I want the displacement. So I have to integrate a second time in order to get my displacement. So that's what we're going to be doing with our calculus. You can do this a lot neater. Just draw your little lines and just write velocity here, and underneath write nothing. And why did I write nothing here? Because that would just be meters times time, meters seconds. It's not a physical quantity we're going to deal with. So both your position or displacement and your acceleration graphs will have just like one piece of information that you need. Velocity is the only one we can go both directions and get something meaningful from. But it will save you dividends in time when you're trying to remember, do I need to integrate or do I need to take the derivative of? Any questions on that?
I have a question about basically the derivation and the information we get from that.
Yeah.
So when we're taking the derivative with, for example, just a position to a velocity graph,
Uh-huh.
algebraically, I guess graphically as well, is there any way to derive a true velocity vector from that aside from just information about direction? Like, is there any way to get components of vector direction? Or is it simply just a matter of we get information about the magnitude and positive, negative velocity?
Okay, so ish, yes. Right, so remember the positive and the negative is going to give us, I mean, when we look at it graphically, we can say, okay, I have a negative slope or a positive slope.
But based on,
No, yeah, no. So you can get how fast you've gone, you can get your displacement, but it doesn't tell us like necessarily where we've gone. Is that what you're asking?
yeah, so it's not really like it's not the most detailed velocity vector in that sense.
Correct, correct.
Okay.
Yep, yep. Good question.
I'm guessing the same is true of integration. When you go backwards, it doesn't quite give you the same.
Well,
Like I know you can get negative and positive based off of
yeah,
like area
what
of
you
below and above
can
axes.
what you can do with those though is then predict at a certain time, so long as the motion stays constant. Now, if I do something like this, where I have a function that kind of looks like this,
Yeah.
then it's like I don't have a constant of anything. Therefore, I can say between like say here and here, I can predict where I would be, how fast I'd be going, and my displacement covered. But that tells me nothing about going on further down.
Okay.
So
Thank you.
you're welcome. Now, I am going to send you into your breakout rooms to finish up looking at this graph and kind of applying the concepts of the area under and the slopes to this. And the one thing I want to remind you of, and it's so easy to forget and kind of get sucked into this, like, oh my gosh, I don't know how to interpret it. If I ask you from say at time 17, time 17 to time 20, am I speeding up or slowing down? Don't forget you have kind of values over here. Now, granted, I don't have specific values there, but I know that I go from 0, so I'm stopped, up to 10 meters per second. So if I'm looking at B, I'm starting at some amount greater than 0, and at 20, I'm ending up at 0. So I'm definitely slowing down. Too many people get hung up on, well, I have a negative slope, so therefore I must be slowing down. And then you get hung up on this one because you say that's a negative slope, so I'm slowing down. And then it turns out you're not. Remember, look at your axes. Let those values kind of remind you of what physical behavior is going on. Don't get yourself sucked into trying to memorize certain things as far as what the slopes mean themselves. Let the graph get you there. All right, I'm going to open up breakout rooms. I want you to deal with the questions on this page. And I want you to remind yourselves that this graph is intentionally vague. So don't get hung up on acute precision. Just, I'm wanting you to get comfortable looking at things both graphically and numerically, and just kind of getting a good feel for what that physical action might mean. Any questions on that? All right.
I had a question about breakout rooms. So some of us are physically together. Can we just, is that going to complicate things for you?
It will only complicate things for me insofar as it would take us forever for me to figure out who to put you with. But there's nothing to say that you can't collaborate between breakout rooms. So if there's a group of you working together, that you won't have easy conversation with others. Does that make sense? Okay. But what I can do, if you know that you're going to work with a group, like get together and work together frequently, is to send me an email and I can create automatic breakout rooms where you guys are put in a group. Does that make sense?
Yeah.
Cool. All right. There we go. Open all rooms. and we'll see you in a few.
The handout just now or some other handout?
The handout just now.
Oh, okay. We got a chance to do it.
Sweet.
Yeah, we went through all the questions.
Awesome.
Group.
All right. So what's the first one? What is the velocity at 5 seconds?
10 plus.
Oops. Something other than eraser. So 10 meters per second. And this is positive. Cool. When is the object moving at a constant velocity?
At
0 to
eight.
10 seconds.
Cool. So I look here, and don't forget, if you're not comfortable with slopes yet, you can always just look at the values that are on the graph. And from time 0 to time 10, I don't veer off that 10 meters per second. So from 0 to 10 seconds is when my velocity is constant. And so then when is the acceleration 0?
The same interval.
Yep. And, I can look at that and remind myself that acceleration is the slope of the line. This is the same as a velocity versus time graph that I'd drawn before. And if the slope isn't changing, then that means I'm not accelerating. Or just remind yourself that acceleration just means the rate of change of velocity. If the velocity is constant, then I have no acceleration. Actually, I should say, if the velocity is constant and my motion stays straight, I need to keep re-emphasizing that. So when is the object at rest?
Only at 20 seconds.
Yep. My velocity is 0 right here at 20. What's the displacement between 0 and 5? So we're right around here.
50 units.
Yep. So my displacement, remember the area under is going to give me my displacement. So that is the area. So 5 times 10, that's 50 meters. What about overall?
200 meters.
Is it 200?
We
think
got
it's
100
100.
meters.
So we're getting two different answers. So is it 200? Is it 100?
I
Distance
believe
is
it's
200.
200.
Distance is 200. Displacement is 100.
Okay, so how are we getting to the 100?
The last 10 seconds, it's moving backwards over the same distance that it moved forwards from 10 to 20 seconds. So it kind of undoes that progress.
Perfect, perfect. So the area here and the area here cancel each other out. So I can have a negative displacement. If that happens, then that means that the only area left standing is this one, which is just the square of 10 by 10. So that makes it 100 meters. Is everybody cool with that? Cool. Does it ever change direction?
Yes, at 20 seconds.
Okay. And how do I know that?
It crosses
Because the
axis.
velocity is positive, then it goes to 0, then it goes negative. So that means it's going backwards.
Yeah, yeah. So remember, if I have a negative velocity, that's just defining, oops, wrong color. That's just defining the direction I am going. Right? So I'm starting off kind of, I'm all positive velocities. So I'd be kind of going something like this, according to this. But now I have a negative velocity. So if I want to just draw in a random variable or a random vector, then that means I'm doing something like that. Am I speeding up or slowing down here in the 20 to 30?
You're speeding up.
Correct. Yep. Starting off at 0, ending up at 10. That means I am speeding up, but in the negative direction. So I am now changing directions. All right. With that, I'm going to stop recording.